So we started with the design of steel beams, wherein we were given the span, which is 6 meters. We were given the service dead load, which is a uniformly dead load or uniformly distributed dead load of 14 kilonewton per meter. Then we have a uniformly distributed live load of 20 kilonewton per meter. In addition to this, we also had point loads. So we had a point dead load of 40 kilonewton and a point live load of 60 kilonewton. And we have to select a suitable section which would be adequate to resist the moment generating because of these loads. So first we started with the calculation of design loads. So all of these are service loads. We need to multiply this by partial safety factors to convert them into factored loads or design loads. So we know that for dead and live, the partial safety factor is 1.5. So we multiply these with 1.5, so 1.5 times 14 and 1.5 times 20. And then the total load is 21 plus 30, which is 51 kilonewton per meter. Now this is the total factored UDL that is active on the beam. And we did a similar treatment with point loads. So this is 1.5 times 40, 60, which is a factored point dead load. Then we have factored point live load, and we just added them. So 150 is the total factored point load acting at the center of the beam. Now, the next step is to calculate the load effects, which is the calculation of bending moment and shear force. Now, we know the bending moment because of UDL is WL square by 8. The maximum bending moment because of point load is WL by 4. So the total bending moment is the sum of these. So we simply did find out the sum, that is 454.5 kilonewton meter. Now this is factored bending moment. Now we also need to find out what is a factored shear force. For a quick revision, I drew this shear force diagrams, wherein this is the shear force diagram for UDL and this is the shear force diagram for a point load at the center. So the maximum shear force is WL by 2 for UDL, therefore we wrote here WL by 2, and the maximum shear force for a point load is W by 2, therefore we wrote here WU by 2. And again we just sum them up to find a value, that is 228 kilonewton. Now we have to select a section that can resist a moment of 454.5 kilonewton meter and a shear force of 228 kilonewton meter, and also a certain value of deflection that we're going to calculate further. Okay, so to select a section, we use the basic, moment formulation for plastic sections. Remember, beta B is equal to 1 for plastic and compact sections. So we assume that we implicitly assume that the section is either plastic or compact, and we say beta B is equal to 1. Therefore, M is equal to ZB into Fi upon gamma M0. Now, we are well aware of this equation by now. We have also looked at the brief derivation. Now, we know everything in this equation except ZB. So, we just rearrange them. So, ZB is equal to M into gamma M0 upon Fi. Now, I told you the importance of matching units. M that we have found out is in kilonewton meter, but Fi is in Newton per mm square. So, you either convert one of them. An easier way would be convert moment into Newton mm. We saw that we'll have to multiply this by 10 power 6, and then this remains unchanged. And the value of ZP that we got is 1,998,000 mm cube. Okay, but when we look at the steel code, we see that everything is in centimeter cube because of limitation of space. So what we did is we converted this mm cube into cm cube simply by dividing it by 1000. So go 3 decimal places here, 1,999.8. Now we have a basic value of ZP. Now we have been saying this from first lecture that ZP is a measure of the bending strength, and therefore we are focusing so much on ZP. So the next step is to select a suitable section. To do so, we went to the steel code. The steel code gives various sections and various values of the plastic section moduli. So we have to select a section that has a value of ZP greater than 1,999.8. So what we saw here is ISMB 500 has a value of 2074.67, which is greater than ISMB 500, which is greater than 1999.8. Therefore, we started with the selection of ISMB 500. Okay, so I believe this is the point where we sort of we did go further, but I believe we paced it a little bit. So I'm gonna repeat things from here on. So now we have selected ISMB 500. Now, in order to find out certain parameters or for calculations, we are going to need some properties of this particular section. Now, IS code already gives you some properties. So these are some properties, and there's some properties that we might need from IS 8, that our steel table, that is IS 808. So the basic properties that are required from our steel from our IS code is that first we need to know the depth of the section, width of the flange, thickness of flange, and thickness of web. So these are the basic geometric properties. So I'll just write them down here. So the first is the total depth of the section, which is 500 mm. Then the width of the flange, which is designated by BF. This is equal to 180 mm. See it here. So this is 180 mm. Then the thickness of flange is 17.2 and the thickness of the web is 10.2. So the thickness of flange is equal to 17.2 mm. Thickness of web is 10.2 mm. Okay. Now, what else do we need? We don't need radius of gyration, but we do need the plastic section modulus. Therefore, the plastic section modulus, what's the value? 2074.67. Z P. Now again, pay attention that this is in centimeter cube. Okay, but for the uniformity of units in our equations, we'll convert this into mm cube. So this is in centimeter cube. This is equal to 2074670 mm cube. Okay. Another property that we need for calculating deflection is the moment of inertia. But this table, unfortunately, does not give moment of inertia. Therefore, we'll have to look into the steel table. So steel table, just find out ISMB 500. So this is our ISMB 500. And this is the value of I that we need. So I have already taken a snapshot here. So ISMB 500, the value of I is 45200 centimeter to the power 4. Pay attention to the units. Therefore, you can call it IZ. IZ is equal to 45200, and this is in centimeter to the power 4. So this is equal to 45200, and you add 4 zeros to it, or you just write it like into 10 power 4. You can write it however you like. And this would be mm to the power 4. Okay, this all is in subscript. Please, write it that way. So now we have all the basic properties. So we started with an assumption that the section is either plastic or it is compact. Now we just have to, this is a small step to, prove our assumption or just make sure our assumption is correct. So what we have to do is we have to classify the section. And for doing so, we have said it multiple times that there's a table in the IS code that helps us classify our section. So this is our table 2, that helps us classify the section as plastic, compact, or semi-compact. Okay. Now our section is an I section. Okay, so we are going to look at the dimensions that are given in this sketch. So first, we have to look at the flange. So this is the outstanding element of a compression flange. And this is a rolled section. So this is not a welded section, or this is not a built-up section. It is a rolled section that is manufactured. Uh, it's a manufactured section. So we use this particular row. So what do we need here? We need the ratio of B upon TF. So what is B? B is half the width of the flange, and TF is the thickness of the flange. That is what we need. For your ease of reference, what I can do is I can just take snapshots, paste it there. So what we need is the outstanding element of a compression flange. Then we have a rolled section. Then we need B upon TF. So our B upon TF is equal to 180 is the total flange width divided by 2. This is our B, and then if you divide this entire thing by TF, which is 17.2. And then this particular ratio turns out to be 5.23. We saw it in the last lecture. And now we have to compare it with these values. So the first value is 9.4 epsilon, 10.5 epsilon, and 15.7 epsilon. Now the question is, what is epsilon? If you go back to this table, it gives that epsilon is 250 upon Fy to the power 1 by 2. Okay, now our Fy is 250. So 250 upon 250 is 1. Square root of 1 is 1. So the value of epsilon is 1, where Fy is 250. Okay, if you want, I'll just make a side note of it. So epsilon is equal to 250 upon Fy plus square root. So since Fy is equal to 250, so this is 250 upon 250 square root, which is 1. And therefore, we now, these values are 9.4, 10.5, 15.7. Now, if we compare 5.23 with these values, we see that 5.23 is less than 9.4 epsilon. Okay, which this 9.4 epsilon is 9.4. And then the second check. Now we've checked the flange. Now we also have to check the web. So this is web of an I section when neutral axis is at mid depth, because ours is a symmetrical section. When the section is unsymmetrical, then you might have neutral axis slightly above or below the axis center line. But here the neutral axis is at mid depth, since we have a symmetrical section. Therefore, we have to look at this particular. Now again, I'll just snip it. So this is a web of an I section. Neutral axis is mid depth, and therefore we'll compare these three values. So now what we need is d upon tw. Now let us see what is d. So d is the depth of web only, excluding the thickness of flange. So d naturally is the total depth minus thickness of flange, thickness of the top flange and thickness of the bottom flange. Therefore, this we need d divided by thickness of web. So this is equal to the total depth, which is 500, minus 2 times 17.2. One flange is 7.2 mm thick. There were two flanges, 2 into 17.2. This divided by thickness of web, which is 10.2. Now this number turns out to be 45.65. We have to compare it with 84 epsilon, 105 epsilon, 126 epsilon. Epsilon is 1, therefore these values are nothing but 84, 105 in this. So this is less than 84 epsilon, which is equal to 84. Therefore, what can we infer from this? You can hear me, right?
The section is plastic.
Now, you're correct. In both these cases, we see that we satisfy the criteria for plastic sections, and therefore we infer that the section is plastic, and this is what we had assumed in the start. So our assumption is correct. Okay. So now, moment ka chapter closed. But we saw that we design a particular section for moment, and then we check it for shear, we check it for deflection. So now, two more steps are remaining. First is check it for shear. Second is check it for deflection. Now, this is what you had done last time, so I'll leave this. Our next step is to check it for shear. Okay. So where do we get this? If we go to the code, yeah. So there is a clause 8.4.1 that gives a nominal plastic shear resistance under pure shear, and that is given by AB into Fy W upon square root of 3. Now, I think you already are aware that whenever shear strength is involved, we divide either our yield stress or our ultimate stress by root 3. Okay. Now, this equation is not very complicated. We know that what is shear stress. So shear stress is equal to shear force upon whatever is the area of shear, whatever is the area that resists shear. So if you have a rectangular section which has a width of say B and a depth of say D, so your tau or the shear stress at any section would be V upon B times D. It is that as simple as that. So this is shear stress, this is shear force, and this is the area of the section that resists shear. Okay. So what we want to find out is V here. We want to find out how much V can it resist. So V is equal to whatever is the shear stress times the shear area. Okay. Now what is the shear stress in this particular case? The shear stress is Fy upon square root of 3. So this is the maximum shear stress that the section can take, and this is AV. Now here we have seen that our web resists maximum amount of shear force, or maximum component of the shear force is resisted by the web, and therefore we add a small subscript here, that is W. So FYW represents the yield stress of web. So FYW upon root 3 into AV. Now the question is, what is AV? So we have seen in our presentation that if it's an I section, if it's a rolled I section, then you can use AV as the total depth times thickness of the web. So this would be FYW upon square root 3. That's 1. And AV is whatever is the total depth and the thickness of the web. Now, obviously, if you are talking about the design shear force, then you will divide this by gamma m0. So this is just a revision, okay? This is not something new, or the formula is, though in terms of absolute designations, it might be new, but conceptually, this formula is not new. So I'll again just paste the snip here. So this is a nominal shear force, but we are talking about design shear force. So the design shear force is equal to nominal shear force upon gamma m0. So this is equal to, or the design shear force is equal to V is equal to AV into Fy. I'm just writing it again. AV into FYW upon square root of 3 gamma m0. Okay. So this is equal to the total depth of the section into thickness of web into Fy of web upon square root of 3 into gamma m0. So why are we saying FYW, and why are we just not writing Fy? So if it's a hot rolled section, it does not matter. These two are equal. But sometimes in a built-up section wherein there's a plate here, and then we connect a plate here, and then we connect a plate here. Sometimes you could use a material here, say number 1, that is different from a material here, say number 2, in order to save some cost. So in that case, Fy of web might be different from that of a flange. But what we are using right now is a hot rolled section. So in an hot rolled section, both of these are same. So, but just for specifying which yield strength, which yield stress are we using, we specified FYW. So this is equal to, the total depth is 500. Then the thickness of the web is 10.2. Then Fy is 250. And we have to divide this by square root of 3 into 1.1. This number turns out to be 736.121 Newton, which is equal to 736.1 kilonewton. Now you have to compare this number with the value of shear force that we found out. क्या value है? 228. This is the demand, and this is our capacity. Okay, so what we see is that this is greater than Vu, which is 228 kilonewton. Therefore, the section is adequate in shear. So ये shear check खत्म. Any questions?
Where did we get the value for tau from?
Sorry.
How did we get tau as h?
Where did we get tau as?
We substituted tau for f. No, sorry, we substituted tau for ht, right? So how did we get that?
HV. What is HV?
ht. That's htw. That's height into the.
Okay, so let me write this again. Perhaps I exchanged their locations and that is why I got confused. So what I wrote is V. So what I wrote is V is equal to A times tau. Okay. So I substituted HTW for A. This is the area. Now, if this is your section, okay, this portion will resist shear, but this portion will resist majority of the shear. Therefore, I replaced it with H into TW, or thickness of the web. And then for tau, which is the maximum shear stress, our maximum shear stress is Fy upon square root 3. That is what I did. So I replaced Fy by square root 3 for tau and HTW for A. So this is A. And this is our tau.
Okay. Yeah. Thank you.
Okay. Questions? If there's anything that you're not understanding, this is the time.
Bhargav, could you go over the annotations again, like the short forms and what the letters and what they actually mean once again? Because it's been a bit confusing watching the
Okay.
thing, and I've just noted it down right for now. But
specifically on this page?
Specifically on this page, but even the little earlier. But yeah, this page was more confusing than the previous. Right now, I've just noted down everything, but I'm not fully understanding where each thing means. So.
Okay. So I'll go slowly. So this N means nominal. Nominal. This P means plastic. Okay. Then V, this V here stands for shear. Okay. Then this is the yield stress Fy of web. It's written here. It's written here also. So this is the shear area. AV is the shear area. V stands for shear, and Fy is the yield stress of web. FIW. Now this D stands for design. So design, anything when we say design, there's a factor of safety involved. Since we are calculating strength, we divide it by factor of safety. So this is AV into FIW upon square root of 3 gamma m0. AV is the total depth of the section, which is denoted by H, and thickness of the web, which is denoted by TW, thickness of web. And therefore, this is HTW FIW upon square root of 3 gamma m0. You already know this. Is that clear?
Yes. I'll just note all of that down.
Okay. So now our last check is remaining. which is the check for deflection. Okay. So for that, I would just go back to this table, which gives us the values of maximum deflection for a point load as well as a UDL. Okay. So for a point load, the maximum deflection is WL cube upon 48 EI. For a UDL, the maximum deflection is 5 by 384 WL power 4 upon EI. This is something that you will have to remember. But just for our reference, pasting it here. So we are going to need this particular equation, this particular formula, and we are going to do this. So now, we saw that when we are checking deflection, we are going to look at the deflection of what the vertical deflection under live loads of floors and roof, and we'll assume that it is that some non-structural elements that are susceptible to cracking, for example, partition walls or ceiling plaster, etc., are supported on this. So we'll limit ourselves to span by 360. I'm sorry, I'll just repeat it again. So we'll assume that this particular beam does not support anything, or does not support a non-structural member that is susceptible to cracking. So we'll limit ourselves to span by 300. This is the limit that we'll use. So the total deflection is equal to the deflection because of UDL plus the deflection because of the point load. Now the deflection because of UDL is 5 WL power 4 upon 84 EI. 5 WL power 4 upon 84 EI. And the deflection due to point load is WL cube on EJ. Yeah. I'll just plug in values here. So this is 5. Now we have to be cautious that this is live load deflection. So while using the value of small w and capital W, make sure that you use only live load. So I'll just write this subscript here. Small w live load and capital W live load. You can perhaps make a note of it that all these loads are service live load. So deflection, the serviceability criteria or serviceability indicator, and we are checking only for live. We use service type 5 into what is WLL by the given data. WLL is 20 kg and capital W, the point is not use these values. These are factored values. We need service value calculating. We need to know the actual deflection at an ultimate. Again,
Bhargav, your voice is breaking a lot. Is anyone else?
Yeah, for me also.
Even because even the Teams icon is not picking up the sound.
Okay, till what point could you hear it?
Service live loads. Where you wrote service live loads on the right.
Okay, service live loads. So if I go back to the page of given data, we'll see that these are our service live loads. WLL of 20 kilonewton per meter and the capital W, which is a point cloud of 60 kilonewton. See, these are service live loads. Do not use these values. These are our factored values. We are interested in deflection at in working conditions. We are not interested in deflection at the ultimate limit state when the section is about to fail. We don't care about deflections there. We care about deflections when the structure is being used. Therefore, we consider either the service loads or these are also called as working loads. Okay, so we'll just plug in these values. So again, we have to be consistent with the units. Now, E is going to be in megapascals, which is Newton per mm square. You will plug in I in mm power 4. Similarly, you will plug in length in mm, and hence this you will have to plug in Newton per mm. So you have to be very consistent with the units. This is a very common error or common mistake that I see in papers, that the units are all messed up. This is in kilonewton, this is in meter, this is in Newton per m square mm, and then get a very ridiculous value of deflection. Sometimes 2 meters, 3 meters deflection for a span of 5 meters. So you have to be always make this habit of being consistent with units. So now let us just do a side calculation here. So we have small w live load. This value is 20 kilonewton per meter. Right? Yes, this value is 20 kilonewton per meter. Now we have to convert it into Newton mm. So what is this? This is 20 kilonewton is 1000 Newton. So 10 power 3 Newton upon meter. A meter is 10 power 3 mm, which is 1000 mm. So this gets cancelled. So the value still remains the same, Newton per mm. So basically, kilonewton per meter or Newton per mm represent the same intensity of loading. Okay. Then what we have is capital W live load is equal to 60 kilonewton. So this is equal to 60 into 1000 Newton. So this is what we'll substitute in the equation. Okay, this is what you should intuitively understand while solving anything. This is not a part of our standard procedure. This is something that you should intuitively understand. So now 5 into W live load. W live load is 20. So 5 into 20 into the span. The span is 5 meters. Therefore, this is 5 meters to the power 4 upon 384. Now, by now, you must be able to recall the value of E anytime. 2 into 10 power 5 is the value of E. And then I. We go back to where we have noted the value of I. The value of I is 45200 into 10 power 4. This is 4500 into 10 power 4 plus capital W. Capital W is 60 kilonewton. Therefore, 60,000 Newton into 5,000 to the power 3 upon 48 into 2 into 10 power 5 into 45200 into 10 power 4. Now quickly give me a number. Now, if you're going to try to find out this value by using your phone calculator, it will take you forever. Anyone? So the value that I'm getting is 3.52 mm. Can someone confirm this value? Okay, I double checked it. We are getting the same value. So this is 3.528, so 3.53 mm. You can make your life easier by taking a step forward. What you can do is you can just take 1 upon EI as common entity in the, so you can rewrite this as L cube upon EI. We've taken this common outside. What is remaining is 5 into small w live load into L on 384 plus this is W live load upon. Now this is easier to solve. So you don't have to use these terms twice in the calculator. You can just take it outside and solve it, and you can get the same answer. So now the question is this deflection excessive or is this deflection adequate? So we already know that delta live load max, which is the maximum permissible live load deflection, is equal to span by 300. So the span is 5 meters. So 5 meters is 5000 mm upon 300. This value is just a second, okay? Just that is why. So the span is 6 meters. Sorry, it is not 5. Sorry that I messed up with the number here. 6, and this is also 6. I wonder none of you got it. You can hear me, right?
Yeah, you can.
Yeah.
Yeah, I'm just like solving it multiple times because I'm not getting the same answer. It's always coming off.
Did you use 6,000 or 5,000?
I used 5,000, but I get the same answer, 3.53.
Okay.
I think I'm just having some of the other calculation errors, some or the other. So I'm just doing it another time.
Okay, you should get this answer. If you use 6,000, then I think the value that you should get is 6.72 mm. Double check it, but you should get this value. So this 6,000 upon 300 is 20 mm. Okay, when we compare these two values, we say that delta, the deflection that we have got, is less than delta live load max. Therefore, the section is adequate. In deflection. Okay, so very simple problem, isn't it? So this might seem like a very long procedure, but I'll just brief it again, and wouldn't seem that long once you solve a couple of problems. So we have loading, we have span. We find out what is the bending moment. We find out what is the shear force. The objective is to choose a section that will satisfy these, or the section that will have the strength greater than these values. So we start with the basic bending formula. Calculate the value of ZP. Choose a section that has the value of ZP greater than this. Q, because naturally, then you will have if you choose that particular section, it will have a value of bending moment resistance greater than this value. Okay, so you choose a section that has a value of ZP greater than this. Note down all its properties, and just prove that the section is plastic, because this formula is valid only for plastic or compact sections. ठीक है, now bending का story खत्म. अभी shear. तो shear के लिए एक simple formula use करना है बस. So the design strength of shear is AB into FIW upon root 3 gamma m0. Values डाली, ये निकाली, compare किया, shear demand कितना है. We found out कि shear demand adequate है. ये हो गया. Second check. Third check, simple, deflection का check. तो deflection में हमको live load deflection देखना है. So while substituting these values, make sure that you service live loads. डाल दिया. Just plug in the values, make sure that units का consistency होना चाहिए, and then the value, just compare it with L by 300. That's it. Do it a couple of times and then you'll be really comfortable with the procedure. There's nothing complicated conceptually in that. मतलब अगर आपको procedure याद है, so you can easily solve this problem. Conventionally, this problem has been in the question paper for about 15 marks. So I think the provided time and the allotted marks are adequate for this kind of a problem. And now at least you know कि जब आप पूछते हो कि कौन सा beam section चलेगा, ये span है, which beam section should I use? This is the calculation that goes into it. Now again, this is the simplest, the simple case है. Actual cases are very complicated. the number of checks that we have to do are also extensive. This is a very simple beam that is laterally supported by actual में सब check करना पड़ता है. Plan check करना पड़ता. Individually we have to check plans, individually we have to check web. Then we have to make sure that the critical moment in lateral torsional buckling is also adequate. There are a number of checks that we have not considered. This is a very simple problem. Okay, so with this, I think we can close the design of steel. Any question? No? Okay.
I have a question. So, but what if it would not have come to be plastic? Like any of the thing would have not when we are proving that it's plastic. Any of the three things, if one of them does not shows that it's plastic, so then do we choose another section and then repeat the steps again? Sorry, all the steps.
So that's a good question. So what you do in that case? See, normally all the hot rolled sections are either plastic or compact, and in very rare cases semi-compact. So the possibility is very less that you will get a semi-compact or a slender section. That is one. And just in case you get or you're not able to prove that the section is plastic, you get a semi-compact or you get a slender section. What you do is you go back here. In this formula, beta B is not 1. But now since you do not know the section, you do not know the value of ZE and ZB. So what you do is, अगर 1900 या 2000 लग रहा है, you choose a slightly higher value. So you choose say 2000, anything that is above 2500. So let's choose somewhere 2700 or 3000. But ये situation आपको नहीं आना चाहिए अगर आप hot rolled sections use कर.
Okay.
Any more questions? Okay, so we will take a short break and then we'll do the honors of conducting a quiz. The last quiz of the semester perhaps. So, give your best. I hope you've learned enough. We have spent enough time in the design of steel beams to, help you surf through the quiz very swiftly. Let's take a short break and then we'll start with our quiz.